Okay, continuing on with the derivation, going from velocity to acceleration of our point with respect to a reference frame. Okay, of course, here we have the velocity of our point P with respect to our inertial frame. Of course, that simply, derivative of velocity goes straight to acceleration with no problem. Same goes with the velocity to acceleration of our inertial frame. That's just moving. But here's where it gets a little bit tricky, and you really have to be careful to keep track of all the terms, what's going on. Here we have the velocity of our point P with respect to our reference frame, the small xyz. Here we have x prime prime times the I unit vector, same with y and z, so that's easy, that's acceleration with respect to xyz. But then we have again this cross product term. We have x times the derivative, or the second derivative actually, of I, j, and k of the reference coordinate system. Excuse me. So we have this cross product term, and next, continuing on, we need to take the cross product of, we'll go back here, take the cross product of omega cross the vector connecting point P to our reference coordinate system. So taking the derivative of the cross product, here is the rule we're going to follow. Derivative of A cross B equals derivative of A cross B plus A cross the derivative of B. So again, this is very involved. It's really, the benefit is just if you sit down and read through it. It's hard to sort of explain this intuitively. You just need to buy it and trust the equation. But once you've figured it all out, you get this term right here. And now we have all the acceleration terms. We want to plug everything in together. And here's our acceleration of our point with respect to the moving reference frame. And the Coriolis acceleration is this term right here that has the 2 omega cross velocity of point P with respect to the reference frame. And it should be no surprise that there's a 2 there, because when you take the second derivative of any term that has a product in it,